Welcome to SS2 Chemistry, Term 3, Week 1. Thermodynamics is the study of heat and energy changes in chemical reactions. Every reaction involves energy, either absorbed from or released to the surroundings. By the end of this lesson, you will define enthalpy and enthalpy change, distinguish exothermic from endothermic reactions, name standard enthalpy changes, interpret energy profile diagrams, perform enthalpy calculations using calorimetry, and apply these concepts to WAEC questions. Let us begin. Enthalpy, H, is the total heat content of a substance at constant pressure. We cannot measure absolute enthalpy, we can only measure enthalpy change, delta H, during a reaction. Enthalpy change, delta H, equals enthalpy of products minus enthalpy of reactants. If delta H is negative, the products have less enthalpy than the reactants, energy is released to the surroundings, the reaction is exothermic, the surroundings get warmer. If delta H is positive, the products have more enthalpy than the reactants, energy is absorbed from the surroundings, the reaction is endothermic, the surroundings get cooler. Standard conditions. Enthalpy changes are measured under standard conditions, 298 K, 25 degrees Celsius, and 100 kilopascals, approximately 1 atm, all substances in their standard states, most stable physical form at 298 K and 100 kilopascals. Standard enthalpy change symbol, delta H with a superscript circle, delta H degree. Types of standard enthalpy change. Standard enthalpy of combustion, delta H degree C. Enthalpy change when 1 mole of a substance is completely bound in excess oxygen under standard conditions. Always negative, combustion is always exothermic. Example, CH4G plus 2O2G, CO2G plus 2H2O, delta H degree C equals minus 890 kilojoules per mole. Standard enthalpy of formation, delta H degree F. Enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. Delta H degree F of any element in its standard state equals 0 by definition. Example, COS, graphite, plus O2G, CO2G, delta H degree F, CO2, equals minus 393.5 kilojoules per mole. Energy profile diagrams show the energy changes during a reaction. The x-axis shows the reaction coordinate, progress of reaction, the y-axis shows enthalpy, H. For an exothermic reaction, reactants start at a higher energy level than products, the curve rises to a maximum, the transition state, highest energy point, then falls to product energy level. The height from reactant level to the peak equals activation energy, EA, for the forward reaction. The difference between reactant and product energy levels equals delta H, negative for exothermic. For an endothermic reaction, products are at a higher energy level than reactants, delta H is positive. Catalyst effect on energy profile. A catalyst lowers the activation energy, the peak is lower, but does not change the enthalpy of reactants or products, delta H is unchanged. Activation energy for the reverse reaction. For exothermic reactions, EA, reverse equals EA, forward, plus delta H. This is always greater than EA, forward, explaining why reverse reactions are harder. Calorimetry is the experimental measurement of heat changes. Simple calorimetry uses a polystyrene cup as an insulated vessel, pour heat conductor, with a thermometer. The heat transferred, Q, to or from the solution is calculated as Q equals mCt, where m equals mass of solution in grams, C equals specific heat capacity of solution, assume water, C equals 4.18 Jg, 1 K, 1, T equals temperature change in Kelvin, or Celsius, the change is the same magnitude. The heat of reaction, delta H, per mole equals Q divided by number of moles of limiting reactant. The negative sign is because if the reaction releases heat to the solution, Q is positive, solution gets warmer, then delta H is negative, exothermic. Worked example, 50 cubic centimeters of 1.0 mol/dm3 HCl and 50 cubic centimeters of 1.0 mol/dm3 NaOH are mixed. Temperature rises from 22 degrees Celsius to 28.9 degrees Celsius. Calculate delta H of neutralization. Moles of acid equals moles of base equals 1.0 times 50 divided by 1000 is equal to 0.05 mol. Mass of solution equals 100 g, assuming density 1 g/cm3. Q is equal to 100 times 4.18 times 28.9 to 22 is equal to 100 times 4.18 times 6.9 equals 2884 J equals 2.884 kilojoules. Delta H equals minus 2.884 divided by 0.05 is equal to minus 57.68 kJ/mol. Standard delta H of neutralization, strong acid plus strong base, is approximately minus 57 kilojoules per mol. Confirming this is a standard neutralization. Sources of error in calorimetry: heat loss to surroundings, heat absorbed by the calorimeter itself, incomplete mixing, evaporation of volatile reactants. Bond enthalpy, bond energy, is the energy required to break 1 mole of bonds in gaseous molecules, always positive, endothermic, because breaking bonds requires energy. Energy is released when bonds form, always exothermic. Delta H, reaction, approximately equals sum of bond enthalpies of bonds broken, reactants, minus sum of bond enthalpies of bonds formed, products. Bonds broken equals energy in, positive. Bonds formed equals energy out, negative. If bonds formed, products, are stronger than bonds broken, reactants, delta H is negative, exothermic. Worked example, H2G plus Cl2G, 2HCl-G. Bonds broken, HH, 436 kJ per mol, plus ClCl, 243 kJ per mol, equals 679 kJ total energy absorbed. Bonds formed, 2 times HCl, 432 kJ per mol each, equals 864 kJ total energy released. Delta H equals 679, 864 is equal to minus 185 kJ/mol. The reaction is exothermic, more energy is released forming HCl bonds than is absorbed breaking HH and ClCl bonds. Bond enthalpies from WAEC data booklet, CH413, CC347, C equals C614, C is identical to C839, OH463, O equals O498, N is identical to N945, HH436, HCl432, ClCl243, CO358, C equals O804, NH391. Key points: enthalpy change delta H equals H, products, H, reactants. Exothermic, delta H negative, heat released, surroundings warm. Endothermic, delta H positive, heat absorbed, surroundings cool. Standard conditions, 298 K, 100 kilopascals. Enthalpy of combustion, always negative, 1 mole burned in excess O2. Enthalpy of formation, 1 more compound formed from elements in standard states, elements have delta HF equals 0. Energy profile, exothermic products lower than reactants, catalyst lowers EA but not delta H, calorimetry, Q equals MCT, delta H equals Q/moles. Bond enthalpy method, delta H equals bonds broken, bonds formed. WAEC chemistry regularly test, identifying exothermic or endothermic from delta H sign or temperature change, drawing energy profiles, calorimetry calculations showing all working, bond enthalpy calculations. Always show units and all steps of calculations.